So the evil deadlock rears its head. Again, as we talked about before, deadlock was an issue when we weren't thinking about distributed transactions, and it even becomes more of an issue now. So let's think about some ways to get around it and what sort of the key issues are that make it difficult. Centralized detection. Centralized detection says that there's some sort of deadlock detector that communicates with these servers that are any server that can be in this distributed transaction system. And what it does is it goes around asking them, what kinds of locks are you holding right now? And it does this on a regular basis, and it gets back this list of locks. So this guy might say, well, I'm server A, and I'm holding a lock on object B, and I'm holding a lock on objects. Let me name these a little differently. Object 1, object 2. I'm over here. I'm server B, and I'm holding a lock on object 3, object 4. What other piece of information do you need besides what you have locks on in order to detect deadlock? What you need locks for. So this one says B. I'm waiting for a lock on object 5. So it might be C. I'm waiting for a lock on object 1, and so on. Now, what happens at this point once you have all that information? What kind of data structure can you pull together very easily with this?
Graph.
Pardon?
Graph.
Excellent. So you have this graph. Now, what property of this graph are you going to look for that to detect deadlock? Cycle. Any cycle in this graph is going to be a potential deadlock. So you guys know how to do you guys probably have like 5 algorithms in your back pocket to do this at this point, right? Okay. So if this graph is, if it's sparse, if it's dense, you can decide what you want to use. What's the problem here with this? What assumptions being made here for this to actually work? Think about our failure model. This is an asynchronous network.
That you don't have processes that have locks that are holding locks that are dead that won't tell you they have a lock anymore.
So that's one of them, is that there may be some. This process may have died, and then it's got, who knows what was. It may die before or after you hear from it, and you have to know what it's going to do with its locks. So let's think about that type of failure, which is either it dies, or what's the other? Even if it doesn't die, what can it do immediately after you've asked for it, that information? It can just change. It can time out, or it can just release the lock or try to get some other lock. So the problem here is that this model assumes that this server here is going to be able to grab a consistent snapshot of the whole system at once. So anytime someone says, I want to grab a consistent snapshot of a distributed system, like exactly. So what can you get into here? You can get into what are called phantom deadlocks or false positives. So you can have a false positive where one of these here, say we had say we had a situation where we held these locks, and then A was also waiting for let's say it's waiting for, let's create a deadlock. A is waiting for 03, and B has 03. So what do we have to have B waiting for to create a deadlock? 01. So let's say what happens is that we come over here and we detect this. And then, actually, let's take this one out. Let's make this example pretty easy. You detect this. So you're like, OK. Then what happens is, by the time you get over to B, A's already gotten rid of this. Right? Then over here, when you get to B, so now you say, OK, well, in the DD here, the deadlock detector is going to say, OK, well, A has 01, and B is waiting for 01. and let's say we have to put one here. A is waiting for 03. A is waiting for 03. So then what happens? Well, you say, well, if A has 01, so you have 01, 03, and A has this one, right? B is waiting for this one. B has 03, then you have a deadlock, right? Because you have two resources that are waiting for these two are waiting. This one's waiting for 01. A has 03. B has 03. B is not going to release 03 until it's got all of its locks. So, boom. But along the way, if between the time that you did that, A released 01, it timed out, or for some, there can be lots of reasons, then the deadlock detector is going to think there's this deadlock around, and it's going to say, deadlock detection, and it's going to go off and try to kill locks or do whatever it can to pull these guys out, even though there was no issue to begin with. So again, the reason this thing that you have this problem is because states of these locks can change as you go through and try to figure out what everybody has, and so there's going to be no consistent global state that you can get at one time unless you quiesce the whole system. Right? Have you guys heard this term of quiescing the system? Quiescing the system means basically you lock down the whole system and say, I'm not going to let anything happen until I figure out what the state of everything is. Right? So, exactly. So that's a great. What's that?
Just driving on a family trip.
Right. Everything. The world stops. So what you so in the middle, when you're creating this type of data structure, it's not going to be, you're going to have pieces of it that are more out of date than others, and you can imagine a deadlock could be created even while this thing is going through, and you won't even see it because something got created after it scanned that piece of the server graph. So centralized systems, centralized type of detection isn't going to work too well. But there are things that you can do to try to help you to not get into these deadlock situations. And one of them we talked about yesterday, which was this two-phase locking. You grab all the locks that you're going to grab before you start your transaction. I'm sorry, you grab all the locks. The strict two-phase locking is you grab everything that you're going to grab before you start the transaction. You do what you need to do, and then you release everything at the end. Standard two-phase locking is a little bit more forgiving than that, which is that you don't release any lock until after you've grabbed everything that you're going to grab. So then you can interleave operations, but there's still this demarcation between when you acquire and when you release. And the reason that something like strict two-phase locking helps you prevent deadlocks is if you're in the acquisition phase and you haven't done anything yet, it's easier for you to as you're trying to get locks, if you get to this point here and you're actually doing the work, then you know that you have all the locks that you need in order to get that work done. If you're in the lock acquisition phase and you're having trouble getting the locks, well, you can always time out and say, okay, I'm releasing all the locks because for some reason I'm not getting all of these. But since you haven't done any work at that point, there's really, the cost of backing out is low. You don't have to go out there and undo a lot of stuff and send a lot of messages out. And similarly down here, you release them all at the same time. If you do strict two-phase locking where you release them all at the same time, then there's no work in the middle here that might cause you to say, oh wait, I have to wait on this blocking operation. So they all get acquired at once, released at once. Remember how we did lock ordering or mutual exclusion ordering? So you can actually introduce priorities. That's another technique that you can use up here, is to say each lock, the locks are ordered. I'm going to grab them in a particular order, and we all of us here have priorities over who gets it over somebody else. So in that point, if you're in the acquisition phase, it allows you to determine more quickly whether or not you're going to be able to succeed or whether you have to wait for someone else to release it. These kinds of things are we've seen before. Some of them are covered in the book. But there is unfortunately, it's one of those things where when someone says I have solved the deadlock problem, you have to really think about it a bit seriously and look at their paper and see what assumptions they're actually making. Let's talk about recovery. So in any kind of distributed transaction system, you have to think about how are you going to recover from failures, and these are the failures that are part of your failure model. So one of the types of failures that you can get, which is the worst type of failure for any type of transaction system, is the server crash. At least if the network goes down, you hope that it's best efforts that you'll eventually be hooked up again. But if you have a server crash and you're in the middle of writing something to disk, anything that's in your memory buffers gets zapped. Anything that's in your Ethernet buffers are gone. The only thing that you're essentially left with is what's written to disk, and who knows what got written. The last few bits are maybe those are unrecoverable. In the System R paper, you'll see that even they had problems with their disks. So we're not going to think about that right now. But if you have problems with your disk, then you have to worry about how to make those more reliable. But this is just bad, right? You get turned off. What we need to implement, as we talked about before, is this all or nothing semantics. So when you've committed, and you've told someone you've commit, your promise is that you've done it all. You've done all the updates that you need to do. And if you say that you haven't committed, then you abort, then you have to undo any type of pseudo updates that you were doing. Just undo all of that. So from the outside, you can see the update or not. So what you typically do is, in order to track all those things, there's three pieces of information for any transaction that you're running, or nested transaction, that you want to keep around. One is object values. So these are the objects that you're changing. You want to know what their original value was, and that's probably stored somewhere, and on disk. And you also want to know what the new values are going to be. So remember the bank account example where we had a new value that we wrote back what the new amount was, that was the balance for the bank. These are the kinds of things that for each transaction, even before you commit it, you want to have this type of information in some kind of state where it can be recovered if a commit has happened and you crash. There's another thing called an intentions list. And this intentions list is you basically, these object values, there's object IDs that are used to name them, and then something that tells you where I can find it. And the reason you need this where is because you can imagine a transaction that's running can write a value, and then it can decide, oh, I'm going to write a different value to it, or I'm going to write a different one. You can also imagine that there might be that the way you structure this, and we'll see later on how this is, the way you structure the mechanism is used for recovery. It could be the case that you have these object values kind of splattered throughout some data structure, and you need to find it. So this could be like an index, or it can be a pointer to some inode. It's just all that matters is that you have to be able to know where that object ID is, so that you can find its value. And then the last thing that you want to be able to track is the transaction status. And that's whether it's provisionally committed or prepared, or whether it's committed or aborted. So let's see if let's look at a more concrete example of how, by tracking these three types of information, how we can get some robustness against server crashes. And one of the techniques that you can use is called logging. And the idea here is that you have this log. If you're someone who's doing involved in distributed in any type of transaction, actually, this works fine for simple transactions. Is you have this log, and what do you put in that log? Well, you put this type of information in there. If someone says I'm going to start a transaction, then that's a transaction status type of record. Okay, so what if during part of this I say write the balance of change the account balance of this account to something else? Oh, okay. Well, what I'm going to do is I'm going to put a value of 30K. That's the new account balance. And then I'm going to put in my intentions list, I'm going to say that this object, I'm going to name it, I'm just going to give it a standard name, balance account. That's a pretty unique name, is at this point in the log. Let's say this is P1. And so I'm going to keep going here, and as there's other objects that my transaction is modified, I'm going to put their values in here, and I'm going to put some kind of intention records that tells me that this object has been modified, and here's where it is, and just keep doing that. Yes.
I'm sorry, I missed the intention is to set the balance to 30,000 or to do what?
Well, yeah, at some point, the reason that you want one of these in here is that when you commit, these changes that are being made to these objects have to be visible to everybody else. And so, right, if the balance is down here, it's stored somewhere down here on disk, right, this is where your current balance is, $100. Right? And right, and so this is the master version of the balance. If you have a lock on balance that allows other people to that keeps other people from reading or writing it, then the transaction system will can put a lock here and say no one can touch this except for this current transaction that's running. You may have a different type of transaction where reads are allowed but not writes, and then in this case you could still read this value and this write here could continue. And so, I mean, it gets back down to the question that was asked before. What are all these transactions about? They're about changing the state of something, of some data. And so, in the end, when you commit, what you're really doing is just committing. You're changing the state of the 10 or 100 or however many pieces of data that are out there. In the date book example, you're changing the state of someone's date book. The 11 o'clock slot from not empty to meeting somewhere in the building. And that's what happens when you commit. So this log is just going to be a record for each transaction that's running of what kinds of changes it's thinking of making if it commits. What you do then is once you get to a point where someone says, I'm provisionally going to commit. So one of these nested transactions says, okay, I'm done, so I'm going to provisionally commit, and there weren't any failures along the way. Then what you do is you write another one of these transaction status records, and you say this transaction is provisionally commit, and it's ID 5. Once you do that, then there's a notion of a recovery manager. So up to this point, what happens if the disk crashes and you have some failure? Well, there's something here that's going to get messed up. But guess what? As long as you didn't reply back to somebody to say, yes, I carried this out, or yes, then that other person, then the other entity that's coordinating this is going to assume that you either had a crash or that the network was down. But there's no guarantee yet that anything's committed or that anything's even been received. Once the coordinator gets back a provisional commit, it has to have some level of guarantee that the stuff that's going to be written out is in some reasonable, safe place. So that's where the recovery manager comes in. Once you write this provisional commit record, what you do is you go through, and in this log, and there can be lots of different records being written in between any of these, you go through and you figure out where are all the pieces that belong to this transaction. So you'll have this piece here. You'll have this here, you'll have this here, you'll have this here, and maybe that's it. Maybe there's only these 4 pieces. And you'll copy these over into the recovery manager. Then what happens is, suppose that someone comes back and says, oh, okay, let's actually commit this thing. Well, what you'll do is you'll say, okay, commit for transaction ID 5. Transaction ID 5. Commit. Once this is forced, once this write is complete and you know it's on there, and it's part of a data structure the recovery manager can access, then you've committed this transaction. Okay, that you can report back a commit. Now there's still work to do, but at that's the earliest point in time. Once this recovery manager has this record here, that you can commit. Yes.
Why do you need the recovery manager?
I was hoping somebody would ask that. Okay, so why? So can someone give me some reasons why you would want this recovery manager? It's redundant. What do you get when you get redundancy?
Fault tolerance.
Fault tolerance. So there's some amount of fault tolerance here. If the media that you're using is unreliable, which in System R actually you got some sense that there was potentially some unreliability, then now you have this data in two places. So that gives you some amount, but there are other considerations.
Couldn't you have a perfectly legitimate transaction which only required a final commit when the server went down, and the recovery manager would then have all of it there and complete it when it starts up again?
Yeah, but you can, if it's redundant here, then you can do that by going through the log. In this case, there's a recovery manager, and the question is why. I mean, one thing you could do is just start munching through this log here whenever you came back up, if you crashed. But what does it buy you to have this separate thing over here? Speed. Okay, that's really important. Remember, speed is important in these things. Where do you get speed? Well, one piece of speed is how fast does it take to do a commit? It's like boom, boom, right? Just 2 writes, you're done. Right? Instead of, imagine if your commit involved having to go through and at some point like figure out what's there, and there's all this work that's got to be done later, which you've already done at the point of the commit. So this record here now is ready to go. It's all in one place. You don't have to go searching through anything. It's there. You can just map these things and do the work. So it makes the commit return faster. Because all this thing is ready to, I'm sorry. The commit returns faster, but you also get when the recovery manager is actually running and saving this stuff, it's all in one place right there. So you don't have to go and start searching for this. Now, what that means also is that this log, remember this, you don't have infinite disk space. So there has to be something that's coming through and cleaning up this log, right? And so let's think about the complication there. If you're coming through and cleaning up this log, there's all these different references that you have to make to see like what transactions have been aborted, and you take all that information out and then you condense the rest of the stuff. It's a lot like garbage collection. Remember you guys did the compression. When you get fragmentation, you can compress everything down. Well, this log here, there's going to be all sorts of data in there about aborted transactions. And to scrunch this log back down when it starts running out of room, you have to go through and find where all these are, and that's expensive doing that. You'd love to be able to have that piece happen independently of being able to run through committed transactions. So if you actually have some other process that has a copy here of what it's going to do, and it's fast, then when you come up here, this log, now the log manager can run concurrently or independently, because this thing's just taking things out. And guess what else? It can start taking out these records here, the aborted ones and the committed ones, because the committed ones are already saved over here. So you get an extra performance boost.
So
yes?
the recovery manager only arises in the case of a server failure, right? It's not going no matter. Is it? I mean, is it running?
Yeah, it'll be running. It's called the recovery manager because whenever things need to recover, something needs to recover, that's what's called. But it is the thing that's actually going to go through and start writing this stuff out.
Then I don't get. You said there's a lot of different transactions in between.
Yeah, there's a lot of stuff that can be going on here.
So I don't understand why the recovery manager isn't simply a copy of what the log, because there's a bunch of different transactions going on. If it needs,
because the only ones that for this log here, the ones that it has to worry about are the ones that are actually, the only ones it really cares about are the ones that it has to commit. Up here there may be a lot of aborts going on. And so you want to minimize any kind of aborts that you have down here, because you want this thing to just, its sole purpose in life is to blast through some contiguous set here and just write that stuff out and be done with it. You don't want it to be going through this huge log where there's a lot of aborts and things are waiting for timeouts, and there's going to be a lot of stuff that's going on up here, hundreds of transactions per second. And what you want down here is like anything that's been able to commit, and it just in a way that it can just blast through it.
How does it know that it's going to get that commit down there before it's reached? Does that mean it's putting the transaction ID 5 start 30,000, all that before it's even reached the commit? So
what it does is it puts when it's provisionally committed, it writes this thing out, and then there's two possibilities. So we haven't gotten to the other one. One is that a commit happens, and the other one is that you get a vote out in it and it's an abort. But what happens in this case if you get some abort there? Well, here's the thing that it is. It's all in one place, gone. Whereas over here, if you want to clean up this log from aborts, you can have all sorts of interleaved values that you have to get rid of, and then you have to do this kind of compression. And over here, you can just blow it away. So there's a lot of the performance issues here are ones that really impact why you would want this type of dual system and the independence here.
So it doesn't actually go into the recovery manager until you're in the provisional commit stage, which is then when you go run through your log. And
that's right. That's right. And the other thing that you get, let's do a little bit of case analysis. Suppose that you're in the recovery manager and you're starting to, and you say, okay, well, I want to, I need to commit anything that's committed here. So what are you going to have? You're going to have some things, anything that's aborted, you can just blow away and you don't have to worry about. Anything that's committed, you have to worry about it in the usual sense. But assume that, let's look at the third case, which is that you have some records that are prepared. Okay, the question is, what do you do with those records that are prepared if you crash? Well, if you crash, let's figure out an algorithm, one algorithm that you could use. One algorithm is, if you crash and you're prepared, then you just keep going and do all the commit, do the recovery manager, make sure the state of everything's inconsistent, and just keep these prepared things around. And just wait for something to come back and say commit or abort. That's pretty straightforward. But let's say you want to have a little bit more robustness in there, because what can happen in that case? What can happen in that case is, suppose that you keep crashing because it's, some sysadmin who doesn't know what he or she's doing and you just keep crashing. Imagine that the recovery manager in that case says, okay, if I keep crashing like a couple times, I'm just going to abort anything in this state unilaterally. So I'm just going to write abort records next to all of these, and I'm going to send these packets out and try to get that out. How does that help you? If you're crashing repeatedly and you say, I'm just going to abort these things that I haven't committed yet. Think about our example before. What was one of the things what was one of the objectives there? Pardon?
To be able to roll everything back.
You want to be able to roll everything back, but remember there's the performance objective. Right? You want these things to be speedy. You want a response back quickly that says yes or no. If this is in a state where it just keeps crashing, or there's some issues that the recovery manager where it doesn't know what it is, it might be better just to abort, because guess what? Someone else out there might have a better way to do it than deal with me, the server who's having all these problems right now. So that's another way where you can this recovery manager, when it's running, it can very quickly figure out what's prepared, what's not. If it feels like it keeps crashing, then it can just unilaterally abort and try to get those messages out as best it can. Better performance that way. Techniques like this the recovery manager, you're going to write it with a lot of assumptions built in. It's going to depend on the reliability of your servers, the reliability of your network, the expanse of your network, how many participants do you think they're going to be in a transaction. All those kinds of elements are going to affect how you end up writing this recovery algorithm. And there's no real rocket science in it, as long as the assumptions are things that you understand up front. And given that you've done algorithms before, it's probably would be pretty easy for you guys to write one of these if you knew what you were writing against. Yes?
I'm just wondering if you'd ever use the recovery manager for things other than just a hardware crash if you're in a distributed system.
Things other than a hardware crash.
I don't know, I was trying to figure out whether, for example, you've got nested transactions, you're waiting on the final commit, there's a timeout, you've got the locks all in place, the timeout says release the locks, so you have to release the locks. So then in theory you should abort, but you could optimize by when you're up again saying, oh, has anything happened to all of that data? No, bang, recommit.
If you have the locks, yeah, if you have once you release the locks, then it becomes, you basically have to abort if you haven't done any of the updates. But if you still have the locks around, then you could say, I'm gonna, if they're still around, then I can still commit. Questions? So there's one other thing that we have to do here if we're doing the two-phase commit. So this logging that I presented here is just is a general model. If you're doing the two-phase commit, remember there's another state that you can have these leaves in, which is this uncertain state, or the one where it's sort of provisionally committed and it's waiting for something to happen. This provisionally commit or uncertain has to be something that is part of this. You write this over here like we talked about in the recovery manager, and analogous to that, the server now has to have something that says done. Now the done commit message will allow the coordinator server to know when one of these things that it has is done, when one of these transactions is finished, and when it is, then it can just it can assume that everybody out there has already communicated that back. It's out there in stable storage, and this transaction is something that I don't need to worry about anymore. Throw it out on tape or on DVD or whatever as a record, and that's it. The main takeaways here are, if you understand the model, understand the issues, there's a lot of work that goes around these transactions, around the phases for committing, and when you start thinking about distributed databases, this type of understanding is the foundation of that. So I don't know if the person who's going to teach that is at what level they're going to teach it, but immediately we start getting into that, these types of protocols are interesting. And the other thing is that optimizing these types of systems isn't trivial. Example, the recovery manager. If you write a recovery manager based on a set of assumptions, and those assumptions start changing over time, the question is, well, do you have to rewrite the recovery manager? Well, your answer might be, well, no, not if I wrote it so that it takes certain parameters the first time. Well, then all of a sudden this recovery manager starts becoming more complicated because you have to give it a lot of different parameters. So then you get into this trade-off of, like, can my recovery manager do everything, and at what point is it going to be unoptimized based on the assumptions for the system? That's a scaling issue, right? As you start building out scaling out, what happens to its mechanisms? So keep those things in mind. The System R paper is a really good example of a place where these guys thought about a lot of these issues and had answers to a lot of these issues, and you go through. And I think it's a pretty fun read in the sense that, they say, here's the problem and here's the answer, and we had all these disks failing, and we hate that if you had a bunch of our installations out there, there's, we're going to end up getting approximately one failure per month, and that really sucks. And they go through all this stuff, so you can really see they're trying hard, and a lot of those things still apply. Thanks very much.